Now, this last example brings us to a particular kind of series. There are different types of series, and depending on the series, some are more well behaved when it comes to finding the values they converge to than others. This last series is known as a geometric series. Geometric series have to have this form, where you're going to see A, which is known as the leading term, and that will be the first term in the series. And then every other term after that is generated by multiplying by some ratio, which we call R. And you can see I just take the previous term, multiply it by R, and I get the next term. Let's skip ahead for a second here. And here's the same series we were just looking at in the previous example. Let's see if we can identify why this one is a geometric series. Well, if it's a geometric series, A is supposed to be the leading value, which is 1, and R is supposed to be the ratio, what we are multiplying by each time to get the next value. Now, if you're really good with numbers, you may be able to see intuitively what that value is. If not, you can form ratios. You take the ratio of a value and the one before it, and you'll get what the R value will be. So if I take 0.001 and I divide it by 0.01, I get 0.1. And as long as I get that same thing when I take any two successive terms, and again, divide a term by its previous term, that represents the ratio. So in this case, the R value that is generating the terms in the sequence that we are multiplying by is 0.1. So that looks a little confusing, but I'm saying I'm multiplying by 0.1. So that's the R value. Now, what's nice about geometric series is we have a way to determine what they converge to. If the absolute value of the ratio is less than 1, we know, number 1, that the series will converge, and number 2, what it's going to converge to. And again, your book will have a proof of this if you want to see the details. Be aware of the fact that if we're saying the absolute value of R has to be less than 1, that's the same as saying R is some number between -1 and +1. So as long as your ratio is between those two numbers, we have a formula, which is a beautiful thing, to find out what the sum converges to. Now, if A is not equal to 0, so if your leading term isn't 0 and your absolute value of your ratio is bigger than or equal to 1, then the series is going to diverge. So we like working with geometric series in particular because they have this nice property. So going back here, we have identified our A and our R value. We now want to check what the absolute value of R is. So the absolute value of 0.1 is, of course, 0.1. And because that is less than or equal to 1, we know this geometric series converges. And it converges to A divided by 1 minus R. We take the A value of 1, divide by 1 minus 0.1, which gives us 1 over 0.9. And if you divide that, you will get 1.1 repeating. And we can also multiply both the numerator and the denominator of this fraction by 10 to get an equivalent fraction. So the decimal 1.1 repeating is actually the same as the fraction 10 over 9. So that's going to be the value that the sequence converges to. And we go back up here, that's what we said in this example. That's what the limit of the partial sums appeared to be. So the formula for the geometric series is a super easy way to find that value that the series converges to. Let's take a look at another series. So we're going to take a look at this series here, and the first thing you're going to want to ask yourself is this a geometric series? If it is, we need to have A be the leading value, And then we need to figure out what we're multiplying to get the next term. So in other words, I have 1/3 times some unknown value has to equal -1/6. So divide both sides by that 1/3, and I get my ratio is -1/6 divided by 1/3, which is the same as times 3/1, which gives me -3/6 or -1/2. So now that I have my first ratio, I need to check a few more and make sure that it does appear that that's what the R value is. So if I take -1/6 and I multiply it times -1/2, I do get 1/12. And if I multiply 1/12 by -1/2, again, I do get -1/24. So my R value is in fact -1/2. I need to check what the absolute value of R is equal to. The absolute value of -1/2 is +1/2, which is less than 1. So I know that this geometric series converges, and it will converge to A over 1 minus R, which is 1/3 over 1 minus, and keep in mind your R value was -1/2. So this is actually going to become +1/2 on the bottom. So I have 1/3 divided by 3/2, which is the same as 1/3 times 2/3, and gives me a convergence value of 2/9. So you're going to appreciate when series are geometric because it becomes a very simple process. We have another test to apply in those situations where we're dealing with series that don't conform to a nice pattern. So the Nth Term Test, which is also known as the test for divergence, says if the limit as n goes to infinity of a sub n. Now, a sub n, remember, is an individual term in the sequence. So if you look at the terms of the sequence in order, if their limit is not equal to 0, then we're going to say that the series based on that sequence diverges. To explain the idea, I'll go back to this first example. So this series is based on the sequence a sub k is 1 over 2 to the k power. So if I list the terms, a sub 0 is 1 over 2 to the 0, which is 1. The next term would be 1 over 2, or 1/2. I can see the individual terms right here. And then the next term is 1/4, and then the next term is 1/8. And notice what's happening here as n goes to infinity. My values on this side, my a sub n's, are heading to 0. My denominator keeps getting bigger, which makes my fraction smaller, which brings it closer and closer to 0. And if those amounts that you're adding together are gradually getting close to 0, your sequence converges. And what this Nth term test says is if your a sub n's are not approaching 0, meaning they're not getting smaller and smaller, then your sequence is going to diverge, which should intuitively kind of make some degree of sense. But we do have to be careful with this Nth term test. It is a test for divergence. If this limit is not approaching 0, the sequence will diverge. This doesn't mean, though, that the series necessarily converges whenever the limit of the individual terms is 0. It's not conclusive. It still might diverge or it might converge. So you have to make sure that you only apply this Nth term test in this way. You can't use it as a test for convergence. So, example 3 kind of outlines that idea. This is the harmonic series. This is a very basic series that occurs in a lot of places and deserves its own name. And the harmonic series, we're letting k take on the values from 1 to infinity of 1 over k. So, my terms would look like 1 over 1 plus 1 over 2 plus 1 over 3. Now we're going to look at two things with this harmonic series. The first being, let's look at the first couple of partial sums. 1 over 1 is 1. That's my first partial sum. Then I add 1 and 1/2, and I get 3 over 2, or 1.5. The third partial sum, I'm adding 1 plus a half plus a third, which gives me 11/6, which is approximately 1.83. Hopefully you understand the process now. I'm just going to skip to the values. S sub 4 should be approximately 2.08, and S sub 5 should be approximately 2.28. So as I let n approach infinity, what number are the partial sums heading towards? Let's look at more terms in Mathematica. All right, I've got the harmonic series stored here, and this initial table, I just look at the first 10 partial sums. And it does seem like, there's only a couple values that begin with 1, but then there's a bunch that begin with 2. If I want to see the first 1,000 partial sums, I can look at every 10th sum instead of looking at every individual. And again, you can see the numbers are still steadily increasing, and it's very difficult to say whether they are actually converging or diverging. We can look at a graph which sort of sheds some light on the situation. It does turn out that the harmonic series diverges. So this is a series that diverges. It turns out that the limit as n goes to infinity of the partial sums is going to continue to increase without bound. However, let's take a look at this nth term test and see what the individual terms are doing. So now I'm going to make my list of individual terms. A sub 1 is the first term, which is 1. A sub 2 is the second term, which is 1/2. A sub 3 is the third term, which is 1/3. And I get the decimal approximations of each of these. And because this is a situation where the denominators are getting larger and larger as we let n approach infinity, the actual a sub n values are in fact approaching 0. But remember, this is the perfect illustration of why you don't want to assume that when your limit is 0, your sequence is going to converge. This is an instance where even though the individual terms are getting smaller and smaller and smaller, the harmonic series actually diverges. So this is the cautionary tale. Make sure that you only look at having the limit of the a sub n's being a number other than 0, and don't draw any conclusions when the limit is 0. All right, so here is one final example. I'm going to write out the first few terms of the series. K goes from 1 to infinity. So we're going to have 1 over 1 plus 1,000, which is 1,001, plus 2 over 2 plus 1,000, which is 1,002, plus 3 over 1,003, plus 4 over 1,004. I can take a look at my partial sums. So here are the first 10 partial sums, and they are increasing slowly at first, and then they seem to be picking up speed. If I go to 100, you can see they're continuing to increase. So I'm not seeing an upper limit here. So it does seem that this might be unbounded, meaning that it's going to diverge. but I can try the nth term test to get a definitive answer. So the limit as n goes to infinity of the s sub n appears to be infinity. Now I can use Mathematica to generate my terms for me as well, because these decimals are going to be pretty small. But instead of using the function that is the sum, if I want to focus on the individual terms, I don't want to be storing my function in that way. Instead, I'd want to say something like, I'll define a of k to be the function k divided by, and you need parentheses around the denominator, k plus 1,000. And now I can ask it what's a of 1. So the first term is 1 over 1001. If I use the capital N function and put it in brackets, it gives me the numerical equivalent. So I can now generate the second term in the series. I can generate the third term in the series, or similar to what I did above, I can just make a table of values. So I put in the table command to have Mathematica generate the individual terms in the sequence. So this is not the partial sums anymore. These are the individual values of 1 over 1001, 2 over 1002, 3 over 1003, and so forth. And if you look at these numbers, I want to see if they are not approaching 0. And I think you'd agree as you're watching, these are not approaching 0. They're getting larger, in fact. If you take some extremely large values, I've told Mathematica to generate the first term in the sequence and then the term that is 100,000 after it. So I'm only looking at every 100,000th term. And you can see these do appear to be heading somewhere. They look like they're heading towards 1. Now, it's not important that I know that. It is important that I know that they're not heading to 0. Because remember, by the nth term test, since the limit as n goes to infinity of the individual terms is not 0, this series diverges. And rather than just looking at the partial sums and saying, I think it diverges, this is more conclusive. So this would be preferred that we use the nth term test. And furthermore, it does appear that the limit as n goes to infinity of the a sub n's is 1. Again, we don't need to know that. All we need to know is that the limit is not 0.